Hello everyone. Today I will talk about our work on 60 GHz mobile imaging. This is a joint work with Yibo and my advisors at UCSB. Today, people control devices. We command drones to fly, we steer the wheel to drive. In the near future, these devices are going to be autonomous. Drones will deliver packages on their own, cars are self-driving, and smartphones can become robots. To be autonomous, these devices need to map or visualize the surroundings, and to do so, they need mobile imaging. Mobile imaging differs from localization. Instead of just locating an object, imaging also tells you the shape and the material. For instance, going through a complex space requires the drone to know the shape and even material of obstacles to prevent collisions. Also, with shape and material, we can prevent some awkward mistakes. For instance, like this one shows here, picking up the wrong item. So in short, we need a mobile imaging system, and the system should have the following requirements. First, imaging must be centimeter level accurate, because mobile devices like drones and objects are already very small. Another example is Google self-driving cars, which already requires 3 centimeter level accuracy in their mapping. Mobile imaging must be robust also. So, we expect autonomous devices like drones to work in various conditions like darkness and rain. And since we're dealing with mobile devices, the system must be portable and affordable. But existing solutions are clearly not suitable. Vision and sound-based solutions either do not work in darkness or can be easily disrupted by background noise. In addition, they cannot tell you the object material. Radar is another option, but when we look at traditional radars, they're huge, expensive, and heavy. Even if we look at modern radars like the millimeter ones we can see in the airport or in the military, they require specialized hardware to do imaging. So a more practical alternative is to leverage the RF radios for communication. And for instance, you may think of Wi-Fi. A lot of recent works focus on Wi-Fi to locate an object, to do hand gestures, and to perform imaging. While Wi-Fi imaging is interesting, it's fundamentally limited by imaging resolution. And it's because of the radar theory shown right here. So the imaging resolution is determined by wavelengths, distance, and antenna array size. For instance, suppose we have a smartphone-sized antenna array that's placed at a distance of 3 meters to the object. Wi-Fi 5 GHz can at best give us a resolution of 1.8 meters. And that means for any object that's smaller than this number, its size can be undetectable. So this is clearly insufficient for our applications. Well, a good news is that 60 GHz radios are available today. So the Qualcomm's tri-band solutions already include 60 GHz with Wi-Fi, and we expect the solutions to be pervasive soon. 60 GHz radios are robust, portable, and affordable. Previous works have verified that they work in darkness and rain, and it's cheap and small with the low cost under $40. The second advantage is that 60 GHz has a stable and predictable propagation. So thanks to 60 GHz high directionality, It has a minimal multi-pass effect that allows us to accurately predict the signals for better imaging. And also, 60 gigahertz has shorter wavelengths compared with the Wi-Fi 5 gigahertz, so it has 12 times better resolution than Wi-Fi. So all of these advantages lead us to explore the feasibility of 60 gigahertz mobile imaging. Remember, previously Wi-Fi gives us a resolution of 1.8 meters. Now we can get 15 centimeters. But we're still not satisfied with this resolution. To further bring down the resolution, we have to find a way to increase the antenna array size. So our earlier work focuses on a traditional radar approach called synthetic aperture radar. And the key idea is to emulate a large antenna array using a small one. Here is an illustration. Suppose we need 1 meter long antenna array for 2 centimeter imaging accuracy, but clearly this is too big for mobile devices like drones. So instead, we use a small antenna that moves and takes measurements at different locations. By doing so, we can create a synthetic array that's similar to the real one. Then we can apply the SAR algorithm to do imaging. But when we actually apply this method to practical scenarios, we find a problem. And that is, SAR is sensitive to the receiver's movement noise. It's sensitive to any movement noise that's larger than the wavelengths. Here we're talking about 5 millimeter for 60 gigahertz. So the movement noise is inevitable. When we command drones to fly straight, it always have deviations and moves in squiggles. Even if we want to locate the drone along its trajectory to try to correct the movement noise, millimeter level localization is impossible. So this type of movement noise will cause the phase error that's used by SAR and gives us a poor imaging result. To show you how bad it could be, here is an example. Suppose we want to detect the object's width. So if the drone moves perfectly straight, we can get an error as small as 10 centimeters, and the longer we move, the better resolution we will have. But when we randomly add 5 millimeter noise to the movement, we observe on average 32 centimeters errors. And this is clearly insufficient for our applications. So the fundamental reason for SAR, the fundamental reason of SAR's problem is that it considers the surface as many points. After the measurement, it will try to locate each individual point on the surface and try to reconstruct the image. To do so, they leverage the RSS and phase information. Because movement noise will cause the phase error, the SAR is sensitive to the movement noise. Our approach differs significantly from SAR. We consider the surface as a single reflection unit. So while the device is moving, it will take measurement and collects the RSS profiles. Because different object surface will have different RSS profiles, by analyzing them, we can obtain the object's location, curvature, width, and material. Instead of using phase, we leverage the RSS and angle variables that thanks to 60 gigahertz high directionality. Because both RSS and angle variables are robust to the movement noise, our approach is robust to the movement noise also. So we named our approach RSS series analysis. And before I go into details about it, let me briefly go over the whole system design. So consider a simple scenario here. We have a drone that tries to detect a nearby object. We also have a transmitter that's either an infrastructure point or another drone. So the first step is to sense the existence of an object. This is done by 802.1180's antenna alignment procedure. So while the transmitter is sending beacons around the space, the signal will hit an object and gets reflected to the drone, let's say on direction 2. Then the drone will tell the transmitter which direction to beam on. Also, based on the incoming signals, the system will tell the drone to move along which direction and about how long. When transmitter focuses beam on the object, the receiver starts to move and take measurements. And then we apply our approach to analyze the profiles to sequentially get the location, curvature, width, and material of an object. Because of the time limit here, I will only focus on the curvature and width. And if you want to know more about the whole system, please read our paper. So to determine the curvature, the basic principle is that the surface reflects the signal like a mirror. Imagine you're standing in front of a mirror. You can see an image of yourself inside there. By physics, transmitter will also have this mirror point. So with different curved surface, the location of the mirror point will be different. Because of 60 gigahertz high directionality, so if we're able to locate this mirror point, then we can tell the curvature of a surface. So because of 60 gigahertz high directionality, we can find the angle of arrivals of the strongest RSS. And then by intersecting them, we can locate the transmitter's mirror point. And then based on the previous object location information, we can determine the curvature and even the radius of an object. So these computations are based on physics and geometry, and we have more details in our paper. So the next step is to determine width. The intuition here is that RSS shape varies with surface width. For instance, a 30 centimeter wide flat object will have the RSS shape that's different from a 10 centimeter one. Here we focus on the normalized RSS to eliminate the reflection effect from different materials. So based on this intuition, we model the 60 gigahertz surface reflection that takes surface width as a parameter. Then by varying this width, we can predict the RSS profiles in real time. And we match the predicted ones with the measured ones in order to find the best match. And the best match will tell you the estimated width. So we validate our approach using our testbed. Ideally, we want to use a steerable phased array, but it's not available on the market. So we use the HXI radius plus the horn antenna and a mechanical rotator to emulate the 60 gigahertz antenna array. The rotator rotates at a unit of 0.15 degree. The phased array have a very similar main beam to the horn antennas. And even if there are side beams for the phased array, they are 15 dB weaker than the main beam. So it will not affect our imaging result. In addition, the total power emission of our HXI testbed is 17 dB weaker than a commodity radius. So we expect better imaging performance when we apply our approach to the commodity radio, to commodity devices. So we experiment with 12 different real objects that has either curved or flat surfaces. By default, the distance between the transmitter and object is 2 meters, and the distance between receiver and object is 3.5 meters. So during the experiment, we randomly add less than 10 centimeters noise to the movement in order to test the imaging performance in presence of movement noise. And we show that we can achieve centimeter level accuracy overall in determining the location and width. Also, within the 39 choices in our database, we can always narrow down the materials to 3 candidates. And here is an example of a curved steel surface. So this definitely shows the feasibility of 60 gigahertz mobile imaging. And in conclusion, we leverage the 60 gigahertz radios to image the objects in presence of movement noise. And this is clearly our first step towards the 3D environmental mapping. And we have a lot of works, a lot of things that to work on in the future. For instance, we show the results of a 1D imaging plus the location information. So in order to get 2D, we need the device to move and cover an area. Also, because our testbed rotation is not real time, our current system focuses on the static objects. Our current system also requires the transmitter receiver to have line of sight to the objects. This is because the 60 gigahertz cannot penetrate most objects and walls. And finally, because our current system focuses on the general shape, imaging the general shape of an object, we cannot tell the fine-grained details about the object surface. So all of these are interesting directions to explore, and this concludes my talk. So thank you, and if you have any questions, I'm glad to answer.